Hey everybody, welcome to this session. My name is Kai Wehner from Confluent, and today I want to talk about a simplified machine learning architecture with an event streaming platform. As you see at the top, we will see how to use Apache Kafka and KSQL together with TensorFlow to do real streaming ML without using another data store or data lake like S3 or HDFS in the middle. So looking forward to talk about that in the next 30 minutes. In the beginning, I want to talk a little bit about use cases for machine learning. By intention, I don't use the term AI, but really focus on things you can implement today. And this includes two different kinds of use cases. First, it's innovative new things to do. That's things like speech translation or face recognition, or maybe even you plan to do autonomous driving. That's pretty cool, and there is use cases and added value around that. But even more important today, you can improve existing business processes with machine learning today already. That's the things you already have in your business, like fraud detection or customer service or predictive maintenance. And no matter what you want to implement with machine learning, today I will show you how to do that in an innovative way with a simplified architecture which scales well without downtime and without data loss. In this example, I took the example of a global automotive company which builds a connected car infrastructure and wants to leverage machine learning. This is just one example, but this is really also possible in a similar way for any other industry. By intention, I used an example where it's about big data, but you can also use machine learning and Kafka for smaller data use cases. In this case, of course, we need to do a digital transformation. And the main motivation is similar to many other industries. Your business is changing, and automotive companies will not just sell cars in the future, but also sell additional services, like predictive maintenance. That's the example I will show you today, how you can implement that at scale for hundreds of thousands of cars with real-time processing and real-time analytics. So in this scenario, we think about a company which already has set up the connected car infrastructure. So you're already ingesting the data in real time and being able to process it. And today we want to include machine learning into that story to do predictive maintenance. So send the driver an alert so that he knows that his engine is probably breaking and he can stop before the cost is much bigger and the engine broke. That's the main idea of this session today, to talk about how to do that. So here we see this on a high-level architecture, the use case. In this case, we have this event streaming platform in the middle and we have a connected car infrastructure. So we already ingest the data from all the different thousands of cars in real time via an integration layer to the streaming platform. And from here then, we use it for different scenarios. For example, for real-time monitoring, so that humans can use the data for analytics or for any decision making. On the other side, the data is also consumed by a batch analytics platform, for example, for reporting, that the management gets new reports every morning. So that's the scenario today already with a connected car infrastructure, not related to machine learning yet. But now, in a second step, we want to introduce machine learning. Let's quickly define what I mean with that. Machine learning allows computers to find hidden insights without being explicitly programmed where to look. So like on this picture here on the left, you really ingest a lot of historical data into the computer, into the data store, and then algorithms train that data to find insights on that. This is not any new thing, so that is things like decision trees or clustering, or maybe even more fancy new algorithms like neural networks, where you can use a convolutional neural network for image recognition, for example. Or we will use in our example an autoencoder to do anomaly detection, so that we analyze the data of the engine of the motor in the car and find out if it will probably break soon. So this is the main idea behind machine learning. It's not really new, but new technologies and new frameworks now allow to do that in the real world easily and at scale in a reliable way. So back to our use case with the connected car infrastructure. Here in purple you see how we add machine learning to our infrastructure. So after pre-processing the data, for example, for filtering in Kafka or for doing enrichment or aggregations, then we send the data into the analytics platform to train an analytic model. This is the first part of machine learning. We train a model, and this model then can be deployed to our application. which in our case in Kafka often it's real time, to use this analytic model to do predictions on future events. So while we have trained a model on existing historical data from car driving, now we use this on new car sensors in real time to predict if the car engine will probably fail soon. Still in parallel, you ingest all the data into other things like a data lake or whatever you want to use that. So this is the setup we want to do, and let's now think about how we can do that. The first analytic model is often built with a tutorial, like if you go to the TensorFlow website, you will use Python, like almost every data scientist today, and you will build a great model, and it takes 20 to 50 lines of Python code. And the funny thing is that really works well to do predictions and to create a great model. Whatever the use case is, image recognition, speech translation, or maybe anomaly detection like in our case. However, the big problem is, the question then comes up, how to deploy that model to production. In real time, to process all the events in real time. At scale, think about the connected car infrastructure, that's millions of events all the time. And this has to be up 24/7, there is no downtime for this. And this now creates a little bit more problems. And we have seen that a lot in the real world, where data science teams build a model with Python and then more or less handed it over via an email to the engineering team, which has to deploy it. And this did not really work for many reasons. Either the production team does use Java as environment for production at scale to be reliable, or simply the Python does not perform well enough, the model, because Python is interpreting the data, and so it's much slower than compiled Java classes, for example. So you have to define a solution for this impedance mismatch. Here's a Google paper, Hidden Technical Debt in Machine Learning, which shows this in even more detail and all the challenges of bringing machine learning into real-world infrastructures. Because the small part which I just talked about, building the analytic model with Python code, that's this black box in the middle, which is pretty small. Because data scientists and also the engineers then, they spend a lot of time, for example, on data collection. So if you ingest all the data from hundreds of thousands of cars in real time at scale, in a reliable way, you can imagine, that's not something what you want to do with 50 lines of Python code. It does not work. On the other side also, when you then have prepared the data and trained the model and want to deploy it to do predictions on new data, this again, it's not just a Python script. You have to deploy it in a reliable way for hundreds of thousands of messages per second. And then you also have to monitor all of that ecosystem. So does my infrastructure work for ingesting and preprocessing and training? Does my model deployment work as expected? And how do we retrain the model and redeploy it? All of this stuff has to be thought about and then of course implemented. So it's not that easy. And so we need a scalable and technology agnostic machine learning infrastructure for that. I think that's clear now. The good thing is there's plenty of examples if you Google on the web. One example is Netflix, and here you can imagine I just choose examples really at scale, so by intention. And Netflix is one example. They have a recommendation engine in the backend to show you the right movies on your iPad or on your computer or on your TV. And every person gets single recommendations completely different from others and in the right context. In the background, this is happening via machine learning and models under the hood, in real time, at scale, without downtime. Uber is another example, so think about that. When you order your Uber taxi, there are so many calculations in the background, and there are big data for millions of users. They have to happen in real time, and they have to estimate things like estimated time of arrival of the driver, estimated time of arrival at the origin where you want to go, estimated cost, and other logistics like pooling, for example. So that's a lot of stuff you have to do, and in the background machine learning is doing that with estimations, and it's really huge and a big scalable project. PayPal as third example, that's more traditional, that's fraud detection, right? So here you have to use different algorithms at scale in a reliable way to make the best recommendations in the end if you decide to accept a payment or say that it's fraud with a specific probability. So this is 3 examples of many, and all 3 of them now connect the dots because they use Kafka under the hood to have a reliable and scalable infrastructure. If you don't know Kafka at all, just on one slide here explaining it, It's an event streaming platform which uses a commit log in the middle. So on the right side, you see the producers append new data to it, and then the consumers can consume the data. So in the end, if you want to explain Kafka in one sentence, Kafka is a streaming platform which combines messaging and storage in a scalable, distributed way. So it's always highly available without data loss, without downtime, because it's a distributed system, and that's very important characteristic. And also it decouples the different producers from all the consumers, and that's very important and a different thing than, for example, a message system with JMS or Rabbit or any other implementation of that. That's why Kafka is used so much here. And with its ability to scale well, it's really built for zero downtime. It expects that some systems are down, some nodes are down, the network is down, but still it continues running and does not lose data. For that, under the hood, it uses distributed concepts like finding a quorum of distributed systems, like using partitions and consumer groups, replication, and many other concepts, which I will not go into detail here. But that's the core foundation of Kafka and why it's so successful in the meantime and used everywhere for many projects. So here you see a good picture where the streaming platform is in the middle, and here you see the key difference. So the central system, it's not a database, and it's also not just a message queue which fills up and then goes down when you consume it. Kafka is a messaging system which in real time can forward the data from the producers to different consumers, right? So it's using the page cache, so in memory, so it's really real time. On the other side, it's also storing these events in an event-based log in the middle, so you can always access these events. First thing, architectures like event sourcing and CQRS, so it's not just a database or a status you update. It's really an event-based system where each event is stored by each event in an unchangeable way in the middle. And this combination makes it so powerful for high scalability and for decoupling the producers and consumers from each other. Apache Kafka was built over 10 years ago by LinkedIn because there was no other solution on the market, and then they open sourced it under Apache license. And now more or less every company on this planet is using it. So here is just a few examples of the tech companies, but there is also many other companies using it in the meantime. So every traditional bank, telco, retailer, insurance company has use cases for Kafka in the meantime. And even more important, and that's really what I want to point out, today, and I talk about 150 customers a year using Kafka, and around 70-80% or so, it's not about big data. So it's not always about terabytes or even petabytes. Often it's about smaller data sets, and you use Kafka for other characteristics. I mean, yes, you can scale later if you need to, if your application gets more important and more throughput, but it's also a very reliable system because it has no data downtime. It has rolling upgrades, backwards compatibility. It's a distributed system with replication, so even if nodes are down, you don't lose data. And with that also, it decouples the system from each other. That's so important to understand this difference from other middleware or messaging systems. And with that, Kafka is used a lot. And therefore here I want to show you just a few use cases separated by the key driver, like increasing revenue or decreasing cost or mitigating risk. So that's the management view on the use cases. And then you can either build your core system around Kafka and your core infrastructure, like not just the Netflix or LinkedIn's of this world do, but also in the meantime, the banks, the insurance companies, the retailers completely rely on Kafka as central nervous system. And then there's use cases for IoT, like you see in the middle in purple, where it's really about big data, like Audi's doing that here. And then there's many other use cases like microservice architectures, middleware replacement, or specific security use cases for online fraud detection or for compliance reasons. A lot of use cases for Kafka. Just as a background, so Kafka came to Europe especially, or also in the US, to many people by ingesting data into a data lake to store the data there forever, for whatever reason. This is just a small use case, maybe 5% of what Kafka is used for. Today it's really used for many other things, and often this is really very mission critical use cases without downtime and data loss. So now coming back to connect the dots to machine learning. Here you see Kafka in the middle, and now I think you can already imagine if you train a model, which is the first part of your machine learning story, you ingest all the data into data storage via Kafka at scale, so that you can train your model at the bottom right. That's the first part of machine learning. And then the second part is deploying your model to do predictions on new data at the bottom left. And here you can hopefully already imagine how much Kafka can help here. But it's not just the Kafka core, which is the messaging and storage layer, which can help here. You can use many additional components which are optional, but which are here to help you. For example, the Apache Kafka project includes Kafka Connect to integrate the sources and things, and using Kafka under the hood. So all the advantages I explained before, like high throughput, high reliability, high scalability, is also used for the integration part. So you don't need to use another ETL tool for that. So you can integrate to both modern systems like Elastic or Hadoop and legacy systems like MQ or mainframes with Kafka Connect. And Apache Kafka also includes Kafka streams for stream processing, so you can do native real-time stream processing with Kafka. You can also use another solution like Flink or Spark streaming, but you can also do it natively with Kafka, for example, on the bottom left, to deploy your real-time analytic models there, to do predictions at scale, like I will show you in this presentation. So here you see how you can use the Apache Kafka open ecosystem as infrastructure for machine learning. Let's now go back to our use case about connected car infrastructures. You have to ingest all the data from the cars in real time into a Kafka cluster. This can either be done directly, for example with Kafka Connect and the MQTT connectors, which are bidirectional by the way, not just ingesting data but also sending data back later to the car or to a mobile app. Or in other use cases, you might have your own Kafka cluster just for data ingestion and then replicate the data to an analytics cluster to separate the critical ingestion from the analytics where you have maybe your data lake or your ML use cases. No matter what, first use case is you ingest your data to have it there for machine learning. A second part, you have to do data preprocessing. That's what a data scientist spends most of the time on. And this is streaming ETL stuff like filtering, transforming, or anonymizing data. That's very common things, and they have to be done at scale because millions of car sensors, right? You have to do that not just in a small Python script, but really at scale for millions of messages per second. So you can also leverage Kafka here. Why not? It's built in your ingestion pipeline anyway, and you can natively pre-process the data, for example, with Kafka streams or KSQL. Right? You can also do some part of the pre-processing in the machine learning framework. So for specific tasks, the machine learning frameworks have better features for you. But for this kind of generic streaming ETL stuff like filtering or transformations, Kafka is the better solution because it scales well and it's built for that. And then just put the smaller data set, which is already filtered, into machine learning, if that makes sense this way. So after pre-processing the data, now we are ready for model training, finally, after all these steps before. Here's one example of pre-processing with KSQL. This is a small query, and in this case we do a filtering. We get all the sensor data into one Kafka topic, and then we filter by Audi A8, which is one specific car, to process that data in a specific stream in a way, for example, to build models just for the Audi A8, if that makes sense in your use case. What's great about this is that you can use this query in rapid prototyping, in pre-processing, and in the quick and dirty stuff, but then you can also deploy this same query to production at scale later. It's just Kafka under the hood. So this query can process millions of messages per second and scales to tens of instances. It's reliable and highly available. It's just Kafka under the hood. And the other thing, what is great about this solves the impedance mismatch between the data scientist that uses Python and Jupyter, for example, like in the screenshots for rapid prototyping. But you can deploy the same model to production, for example, with the Java engineers, which have the GVMs at scale for Kafka. And so this impedance mismatch is solved here. So different technologies for development and production deployment can be used. And under the hood, you deploy the same query or the same Kafka application. So that's pretty cool, I think. So finally, after pre-processing the data, we can ingest the data into a data store because we want to do the model training as one part of that, right? Here you see we use again Kafka Connect to ingest the data, in this case into Google Cloud Storage, because in this example we are on Google Cloud. This is the object store where we store all our historical data to do the model training later. This is batch typically, right? It's a lot of data. In parallel to that, we have other consumers, which are completely decoupled from that. And for example, here we see Elasticsearch, which is building indices in near real time. And we have a real-time time series database. And maybe we have other consumers which process the data in Kafka. It's all decoupled. That's another advantage of Kafka. But we, in this case, focus on the storage part in Google Cloud Storage because we want to train our model here. So finally, we are here in this case. This is also where the cloud is great because it's elastic. We can spin up new instances with GPUs or even TensorFlow processing units to process the data at scale and train our model, maybe with deep learning in TensorFlow, maybe for a few hours, and then we shut down the instances again. Just pay as you go in the cloud in an elastic and scalable way. So here now is really where these 20, 50, or maybe let it be 200 lines of Python code are. They train one or more models and compare them and build a binary out of that, which we can then finally use for predictions on new events. So this is one example of a model. As I said, in this case, we are using predictive maintenance and we are using an autoencoder. On the left side, you can see how that works. We get all the input data into the model from all the sensors. And then this is an unsupervised machine learning algorithm. So this is compressing the data and then it's trying to decompress the data again to the output. And if this decoding works well and the output is the same as the input, then everything is working normal. We don't have any anomalies. But if the decoding does not work well, then this is insights that we have anomalies. This is how autoencoders, one specific unsupervised deep learning algorithm works, and that's perfect for sensor analytics in our case. Because when sensors send strange data with anomalies, then we can decide if this is probably an engine problem and we can send an alert to the mobile app of the business user. On the right side, you see how that looks in TensorBoard. So this is just a simple example of how such a neural network looks like. And under the hood, and that's important, this is just a binary. In case of TensorFlow, this is protobuf file. So in case of another framework, it may be Java code or XML or proprietary. But the point is, this is a binary. So this is now trained. And in the second step now, we can deploy this model somewhere else, completely separated. Before I talk about that, one more point here. So when you train models, you typically have a data store. And the title of this webinar here is Simplifying the Architecture. And this is now what you can do. Because instead of storing all the historical data in a data store like S3 or HDFS, you can now directly stream the data from the Kafka log into TensorFlow. This is used using TensorFlow I and the Kafka plugin. So it's a component of the TensorFlow framework. And that's really pretty cool because you can do direct streaming ingestion for model training. So you simply don't need the data store or data lake in the middle for machine learning. You directly ingest all the streaming data from the cars via Kafka into TensorFlow. And as you can see here at the bottom, to train one or more different models with TensorFlow. That's pretty cool, isn't it? You don't have to do that, but it's just an additional option to simplify your architecture when you don't want to use a data store. No matter how you train your model with or without a data store in the middle or with real streaming ML, now you want to deploy your model and do model inference for predictions. And this can be completely separated, and that's also pretty important because we can, for example, ingest all the sensor data from the cars into the cloud, do the model training in an elastic and scalable way here. And then again, we have just a binary as model and we deploy that somewhere else. For example, at the edge. Whatever that means. In the case of a connected car infrastructure, it can be data centers in specific regions at the edge, in the proxies, or it can be really at the edge in the client, which is the car in this case. So there are two different options of how to deploy analytic models. From a data science perspective and product perspective, often people recommend to use a model server, like you see here on the right side. Every analytics tool, no matter if open source or proprietary, has a model server. So you deploy your model to your model server. In this case, this is TensorFlow serving the model server of TensorFlow, and you deploy your TensorFlow model there. This can either be hosted by yourself at the edge in a data center, or maybe in Google Cloud where you can use the Google machine learning engine for that, which is a hosted TensorFlow serving under the hood. And then you use your Kafka streaming application here on the left side, and whenever new input data comes in, then you send a request to the model server with the input data. There the model is applied for the inference, and then you get your prediction back to the Kafka application and process it there in your Kafka topics and any other logic coming after that from other Kafka consumers or external applications. This works very well and it's pretty simple. The big problem here is that you always have this RPC call in the middle. You always have to do a request and a response. In case of TensorFlow serving, at least, it supports gRPC, which is a good technology. It's a robust and a good scalable and performant RPC protocol. Most other model servers only support HTTP here, which is worse performance and not really good scalable. Anyway, even if it's gRPC, you still have to do this RPC all the time. And you have to think about, what if the network is not working well? What do we do with error handling? So what do about side effects if we use exactly one semantics in Kafka, but always do this kind of RPC in the middle? That's actually an anti-pattern in Kafka in general, not necessarily just for machine learning, but in general, it's an anti-pattern for Kafka applications because they are streaming, not RPC. It works well in some use cases, but especially at scale, like in a connected car infrastructure. I typically recommend to really embed the model directly into your streaming application. It doesn't matter if it's a real stream processing engine like Kafka Streams or KSQL, or maybe just a Java or Go or Python client. But you can embed your model directly into that application so that it's just one pod or container or engine you have. It's not an RPC call to a remote engine, which you have to do. So this is much more robust and scalable and performant. And in many solutions, especially like in a connected car infrastructure for millions of sensor events per second, this is the better solution in my opinion. But both have their trade-offs, so pick what you need. Here's one example of an embedded model. In this case, I used KSQL. I built a stream with anomaly detection, and here I just picked the sensor ID from the specific engine of each car and use a user-defined function to detect the anomaly on the sensor values. So the sensor values from this engine go into that function, and under the hood I have embedded the TensorFlow model. I trained it completely separate in the cloud and embedded this in this small lightweight microservice here, which could be deployed either at the edge in a proxy or even directly in the car here. And this query here is very simple but scales to millions of messages per second, and it's robust, it's scalable, reliable, and has no data loss if you configure it the right way in Kafka. So that's pretty cool and easy, isn't it? So if we now go back to our architecture from the beginning, now I have dedicated technologies and components everywhere. In this example from the left side, we ingest the data via an MQTT proxy. So this can be different technologies like Kafka Connect with MQTT connectors, or this can be a specific MQTT proxy like from Confluent, or this can be a specific MQTT solution, which you can deploy somewhere else and connect that to Kafka in some kind of way. Then you ingest all this data in real time and do some pre-processing with KSQL in this example as discussed for filtering or anonymization of the data. And then you send the pre-processed data directly to TensorFlow. As discussed before, with TensorFlow I, you can directly stream the data into TensorFlow without the need for another data lake in the middle. And after model training here, you deploy your model somewhere. As I said, either in an embedded Kafka Streams application to do real-time predictions at scale, or maybe directly in the car, whatever your use case makes sense of. And with that, we can send real-time alerts to the user, like to the mobile app or directly to the car and say, hey, please stop your car in the next 10 minutes because probably the engine will break otherwise. And in parallel to all that, you can also ingest, of course, the data somewhere else, like in an Elasticsearch for analytics or reporting. That's the beauty of Kafka. There's many different consumers typically of data. Some batch, some real-time, some near real-time. They're all decoupled, and it doesn't matter if you add more consumers. The performance of all the others does not consider that. They do not care about this one. It scales well even with more consumers. So here's another picture of the same architecture. This is a demo we have built actually. It really connects to 100,000 cars. So this is not a Hello World example. This shows how you can build this in production pretty easily. So we have set up this demo in around, I didn't count the days, but it was around 15 to 20 man days, which we spent to set up a complete infrastructure running on Kubernetes, where we scale the different components independently. So we have on the left side the clients. This is of course simulated clients, which are also running in TensorFlow here. But this really simulates 100,000 connections. And these 100,000 connections send data to the MQTT cluster. In this case, we use HiveMQ, which is scalable and robust MQTT cluster and product. And from that, we ingest it into Kafka, like we discussed before. And here we do our processing, our model training with TensorFlow I/O and streaming ML, and then we deploy the model somewhere. And here we have used different examples, like you can either directly do the model predictions also in the same Python application with TensorFlow I/O, or you can deploy it to a TensorFlow serving model server, or you can embed it in Kafka Streams or KSQL, or maybe even directly in the car, which is then, for example, TensorFlow Lite and C code at the site in the car, right? And this is all built on top of Kubernetes, so it scales well and shows a lot of these features. It's pretty cool. By default, we are running that in Google Cloud Engine, but that's really possible everywhere, and that's why we build it this way. We use Terraform for that, and by intention, we let you configure everything of that. So please feel free to try that out and share your feedback and how you think you could use that. It's not just for connected cars, but for any kind of IoT scenario, how you can use it in the same way at scale. So for manufacturing or for mobile apps, where you have millions of mobile apps, you can use MQTT in this case. So with WebSockets then. So there's plenty of use cases. Just check out the GitHub project here and let me know what you think about that. Regarding GitHub, I have also many other examples which are not that sophisticated like this use case, but more simple ones. For example, where I show you how you can deploy a machine learning model in a Kafka Streams or KSQL application. And I don't use just TensorFlow here, but also H2O with Java classes, for example, or deep learning for J. And I also have an example with TensorFlow serving, so where you have your real model server separate from the Kafka application. So that's some pretty cool examples, which I recommend you to check out if you're more interested in that. And with that, let's finish with the key takeaways. So you really shouldn't underestimate the hidden technical depth in machine learning systems. Everybody who has built these systems at scale can confirm that, right? So it's not just about building the model, which you have seen in 50 lines of Python code, but really building the whole infrastructure with data ingestion, data pre-processing, model training, model deployment, monitoring all the infrastructure. It's not that easy, so don't underestimate that. And that's why Kafka plays such a big role in machine learning infrastructures at scale and in flexible infrastructures. So that's really the common use case here. Use Kafka where you need it. You can even train your model like you do before with a data lake and with Spark maybe, but completely separate it, then just deploy your model to a Kafka application and monitor all of that in real time. Or you build the whole infrastructure with Kafka. It's up to you what makes sense in your use case. And therefore it's really cutting edge technology if you want to use streaming ML with Kafka and TensorFlow I/O. This really simplifies your machine learning infrastructure because you don't need this data store or data lake in the middle like S3 or HDFS or a Google Object Store, right? So that's really cutting edge and pretty cool, and I recommend you to check that out. And with that, in this around 30 minutes, I hope this was a good overview about the relation between Kafka and the streaming platform and machine learning tools like TensorFlow and how to build scalable solutions with that. If you have any questions or feedback, please let me know here on YouTube, or please connect on LinkedIn and on Twitter. And hopefully we see each other in other videos and blogs. For example, I will also do another video and blog post about the demo I talked about before with the 100,000 connected cars and streaming machine learning. That's what I will build a dedicated video and blog post for. So thanks for watching and see you soon.